board and remove this stuff, so we don't need it for the next bit. And talk a little bit about how different observers perceive events. So, if we draw an event here, this is just an event, and it has some, and it can be anything, it's any event. And let's say it has some coordinates, and those coordinates are CT and X. Right? Those are the time of the event and the position of the event as observed by a particular observer. Now you can have another observer who's moving with respect to this observer. So if we call the observer who measures CT and X the unprimed observer, it is possible, and in fact, well, you see it in relativity all the time, that a different observer who's moving with some velocity relative to the first observer will see different coordinates for the same event. Okay, and that and you can calculate, if you know the velocity of the second observer with respect to the first one, you can calculate the coordinates measured by this second observer in terms of the coordinates measured by the first one. So let's, instead of talking about first and second all the time, let's do what we did in the course and talk about an unprimed observer for whom the coordinates are CT and X, and a primed observer for whom the coordinates of the same event are CT primed and X primed. Okay? And so there's a transformation called the Lorentz transformation between the coordinates in the unprimed coordinate system and the coordinates in the primed coordinate system. And that transformation is this one. It's, for the time component, we have CT primed equals gamma, which we'll talk about in a minute, times CT minus beta x, and again I'll talk about beta in a minute. And then for the position coordinate x prime, that's equal to gamma times x minus beta CT. And we're assuming that the relative velocity of the primed observer, the observer carrying the prime coordinate system, with respect to the unprimed observer is parallel to the x-axis. And if that's true, there's no difference between the primed y and z coordinates and the unprimed y and z coordinates. And so we just write y primed equals y, z primed equals z. And so this set of transformations are called Lorentz transformations. Right, so what does that look like geometrically? How is that possible? Well, the answer is that in relativity you can overlay the axes of the prime coordinate system on top of the unprimed coordinate system axes. And when you do that, you discover, and we talked about all this in lectures, that the primed CT axis, CT primed, is rotated with respect to the unprimed CT axis, and the prime x-axis is also rotated in the opposite direction with respect to the unprimed x-axis. And so if we wanted to read off the primed coordinates of this same event with respect to the unprimed coordinates, to do that you draw, just like we drew this dotted line parallel to the x-axis to get the CT coordinate, we do a dotted line parallel to the x primed axis to get the CT primed coordinate. So let's do that. Let's make a slightly different dot. So this dotted line is meant to be parallel to the x primed axis, and this point of intersection here is the CT primed coordinate of the event. And similarly, to figure out the x primed coordinate, we do a dotted line parallel to the CT primed axis. So that line there is meant to be parallel to the CT primed axis, and this intersection point of this dotted line with the x primed axis will be the x primed coordinate of the event. And you can see immediately that the CT primed and x primed coordinate system is skewed with respect to the CT and x coordinate system. And the skew is such that the angle through which the CT primed axis is rotated with respect to the CT axis is equal to the angle which the x prime axis is rotated through with respect to the x-axis. So if we call this angle alpha, say, then this angle here is alpha as well, and they're the same. And when you think about it, for different amounts of relative velocity of the primed and unprimed observers, you're going to get different amounts of this rotation. And the ultimate is for very fast-moving primed observers, these two, the CT primed and the x primed axis, will rotate around more and more until they actually meet. Where do they meet? Well, they meet at 45 degrees. Which means that all observers agree on the equation of the world line of a photon, because for every observer, the equation of the world line of a photon is, well, for the unprimed observer, it's x equals ct, and for the primed observer, it's x primed equals ct primed. And for the double primed observer, for another one, moving at a different relative velocity, x double primed is going to be equal to c times t double primed. In each case, the gradient of the world line of the photon is the same. So everybody agrees, in this way of looking at things, everybody agrees on the world line of a thing moving at the speed of light. And that's all consistent with Einstein's fundamental postulates of relativity, one of which is that the speed of light is the same to all observers. So that's the end of my section on Lorentz transformations of position and time coordinates, and how coordinate systems and relate to each other, and how to draw a space-time diagram, and also how to draw world lines and events. So what we'll do next, after I've taken a break and got my act together, is go through some of the examples which I did for various different purposes towards the end of the course to help you prepare for your exam and to help you learn the material for yourself by self-study, which is what you're meant to be doing.